In this video, we're going to talk about gravitational fields. You'll learn about the concept and how we calculate it, and also why is G 9.81 newtons per kilogram on Earth? Why is it different on other planets? If you wanted to find the gravitational force of an apple on Earth, you could use Fg equals mg. G is what we call the gravitational field strength, and a good starting definition is that it is a space of gravitational influence. So whether there is an apple there or not, there is a gravitational field. If you were to zoom out a little bit, you would also be able to use Newton's law of universal gravitation to solve for Fg. We'll call the apple's mass little m and the Earth's mass big M, and by using Fg equals big G times m1 times m2. m1 will be the planet's mass, m2 will be the apple divided by d squared. We can also find the gravitational force upon this apple as well. Now, when we talk about the gravitational field, we're talking about this value right there, that little g here. So on Earth, if you know the mass of an object, you multiply it by what we call the gravitational field strength, 9.81, we can get the weight of the object. We can also use Newton's law of universal gravitation to calculate it as well. Now, if we set these equal to each other, which we can because both of these equations are calculating for the gravitational force, we notice that the mass of the apple gets canceled out. And we get something interesting. We get that little g, which is the gravitational field strength, is equal to big G times the mass of the planet, which is Earth, divided by d squared. And this is the equation for gravitational field strength on a planet. Using the equation that we just derived, we can substitute Earth's mass, which is 5.98 times 10 to the 24th kilogram, and Earth's radius, which is 6.37 times 10 to the 6 meters, into our equation and calculate the gravitational field strength on the surface of the Earth. And when we calculate this, we get 9.8 newtons per kilogram. And this number looks very familiar because this is the gravitational field strength we use to calculate the weight of something on Earth. So when you use the equation Fg equals mg on Earth, this number is what we substitute for G, the gravitational field strength. So to answer the question, why is G 9.8 on Earth? The answer has to do with because of the Earth's mass and the radius of the Earth. So you can see in the equation that the gravitational field strength is related to the mass of the planet divided by the radius of the planet. If the Earth had a different mass or a different radius, then the gravitational field strength would be different. So you could see how it could be different on a different planet that had a different mass or a different radius or a different mass and a different radius. The next thing I'd like to do is to give you some representations of this equation so you can better understand what this equation is telling us about how the gravitational field is related to the distance. So one way to understand this relationship is to use what are called gravitational field lines. Now, we cannot see the gravitational field. If you look around the room, you cannot see the gravitational field. It's not visible to us, but we can use these lines to help us understand where is this gravitational field stronger or weaker. And so where the lines are closer together, that's where you have a larger gravitational field. And where the lines are further away from each other, that's where you have a smaller gravitational field. And this makes sense because if you look at the equation, the gravitational field is proportional to 1 over d squared. And sometimes you'll see people use r instead of d, but it's the same thing. It's just the distance to the center of the planet. And so this is an inverse square relationship. If we drew a graph, and on the y-axis we had gravitational field, and then on the x-axis we had the distance from the center of the planet. So let's say this is r and 2r and 3r from the surface of the Earth, and this would be 9.8 on the surface of the Earth. As you move away from the Earth, it's going to decrease because it's an inverse relationship. Now, an interesting side note is what happens if you go into the Earth? Now, that's beyond what we can do with this equation. You're going to need some calculus here. But if you were to go into the Earth, if you were to go from the surface and you go in towards the center of the Earth, the gravitational field would actually decrease, which is kind of weird, right? Because when you're outside the surface of the Earth, as you get closer to the Earth, the gravitational field increases, but as you go into the Earth, it decreases. And that's because when you're inside the Earth, you have masses above you and you have masses below you. They're pulling you in separate directions and in opposite directions, and they cancel out. And so if you're at the dead center of the Earth, the gravitational field strength would be 0 because you have masses all around you pulling on you. And essentially your net force would be 0 because you're being pulled equally in all different directions. So a question you might wonder about is, what if you were to dig a hole and jump into the hole and into the Earth? So you dig a hole into the Earth all the way to the other end. What would happen? So as you fall in, you would speed up, and your acceleration would start to decrease. It would start to decrease, just like on this graph. Once you reach the center of the Earth, your acceleration will be 0. But because you've built up a lot of speed here, now you're going to keep moving, but you're going to slow down. So your acceleration will be upward. You're going to slow down. And once you get to the other end of the Earth, you will return back to a speed of 0. So you're going to jump in here, you're going to speed up all the way to the center. Once you reach the center, you're going to start to slow down all the way to a speed of 0 when you get to the other end of the Earth. Now we're assuming that there's no air drag here, and we're just assuming an ideal situation. Now a question you might wonder is whether or not G is 9.8 newtons per kilogram, or G is 9.8 meters per second squared. Is gravitational field the same thing as the acceleration due to gravity? So this is a great question. So I want you to know that as far as the units are concerned, these two are equivalent, because a Newton unit is simply a kilogram meter over seconds. So that's what a Newton is. It's a derived unit and meter over second squared. So Newton is a kilogram meter over second squared. And the way I remember that is I remember at F net, right? F net equals MA. And M is kilogram, A is meters per second squared. So a Newton is equivalent to kilogram meters per second squared. So if I took Newton over kilogram and I substituted kilogram meter over second squared divided by kilogram, what you notice is that the kilograms cancel out and we get meter over second squared. So these units are equivalent. A meter per second squared is equal to a Newton per kilogram. So numerically, the gravitational field strength and the acceleration due to gravity are the same. They're both 9.8, but they're conceptually a little bit different. Gravitational field, we're asking the question, how much gravitational force is exerted per unit of mass? So this allows us to calculate using Fg equals mg. If we know the mass, we can use the gravitational field to calculate the gravitational force. On the other hand, the acceleration due to gravity is telling us the acceleration of an object only under the influence of gravity. So numerically, they're the same. Conceptually, they're a little bit different.